Okay, sorry for the late start. Just trying to work out my share screen here. Okay, so we started right this last time, but let's just kind of review a little bit. And also, this is not like really a complex topic, but there could be some small subtopics, right, that we went over, that we will go over, that may be, right, sort of like, I don't know, right, lost in translation or something. So I just want to list out, right, the topics that sort of are crucial, right, to master for this lecture. Of course, joint distribution, right, is the main topic. But then, right, from joint going to marginals, right, is an important, let's say, subtopic. Independence, also from joint to expectation, right? So basically, right, all these come from, right, the joint distribution. And so basically, right, knowing how to derive them or like how they're connected to joint distribution is the main topic here. Or I guess it's the point here. Okay, so joint distribution, right? At the heart of it, on the surface, right, might seem like a multi-valued, right, distribution function, meaning that, right, it's a vector value, right? You describe the distribution on 2 or 3 dimension, okay? But that's sort of one way to look at it. A more intuitive way,
Professor,
possibly, yeah.
the screen share is not on yet.
Oh God, this just keeps happening. I am very, very sorry. It's not on yet. It's actually on my side. It doesn't seem to show on your side. Yeah. So sorry. Okay, give me a moment, all right? Very, very sorry about this. Does it work now?
Yeah, it's good now.
Okay, good. Really appreciate that. Yeah. Otherwise, I would not know. It did show on my side. Anyway, yep. So back to right here are the topics. Okay, that are basically the ones that we will go over. All right, in this lecture, or sort of gives you an organized, like, overall view, right, of the points to pay attention to. Okay. And basically everything here, right? To put in one word, they all come from joint distributions. And joint distribution, right, is basically a vector value, right, distribution. But a more intuitive way to understand this would be describing the interaction, right, of the random variables x1 to xn. Now, a lot of times in this class, we'll limit to n equals to 2, right, and we'll go to n equals to 3 at most. But you understand that the framework, right, everything we discuss here works for higher n, right? There's nothing to stop whatever we discuss here, right, to generalize to higher dimension. And that's why this is super important because, right, when you look at statistics or anything like that, you never look at one single random variable, right? You look at multiple random variables together. So joint distribution is always the topic, even if it's not spelled out explicitly, right? And yeah, this also will be a common example. These two, actually, there are 2 examples, right? uniform on the square, it can be rectangle, and uniform on a circle, okay? And basically, they are sort of easy examples to look at for continuous joint distribution. And they highlight, right, the point that they are just like two-dimensional distribution, right? It's easy, a circle or a square. But just the difference in the region would mean different things, right? In terms of the interaction between X and Y, or X1 and X2, right, is the message. But of course, there are other distributions that we'll look at too. Okay. So even though, right, not joint distribution can cover everything, meaning that, right, you can have a joint distribution between one discrete and one continuous random variable. To make things easy, we'll just look at when the two cases, when all of them are discrete and all of them are continuous, right? If all of them are discrete, then we have something called a joint PMF, right? Joint mass function, okay? Which basically, right, gives the probability that they take all possible values, right? And one thing that you would notice that we start doing here, or at least I start doing here, is I can't describe everything, or I start to be a little bit vague about the values. The reason is very simple, right? If there are n dimensions, then the number of values will be something raised to n power, right? Listing all of them out even verbally would sound very boring and tedious, right? So I'll keep saying things like all values, but that's where the danger comes, because you have to understand what I mean, right, when I say these things. So feel free to ask, right, if something is unclear, okay? So yeah, right, the sum over all possible values must be 1. Right? And this is a plot of two-dimensional distribution, right? Nothing crazy here, actually, right? And this plot, I would argue, has not much values, but it serves as kind of a contrast, right, to the joint PDF, where it's a surface, right, over a region, more like your calculus 3, right, sort of picture. A joint discrete distribution would be spikes, right? Which you don't see in calculus 3 because there's no reason to look at spikes, right? But there they are, right? So this table right here, right, would have much more value because it gives a picture, right, quote unquote, for two-dimensional, right, jointly discrete random variables. And the information here, the way we approach things here actually generalizes to the jointly continuous if you understand what the change should be, what the changes should be, right? So first of all, right, it's a two-dimensional table, right, that lists out, right, the values, right, for the pair of numbers. So here, right, these two random variables, you can say, are distributed over a rectangle, right? Because X is value from 1 to 4 and Y value from 1 to 3, right? It's a rectangular distribution. Why do I say that? Because again, right, the region doesn't have to be that way, right? It's kind of natural for discrete random variables to have rectangular shape, but the shape can be a circle, right? Circles are like an awkward shape to use in discrete, but it could be, right? Anyway, so this table like this doesn't have to be the picture, but at least it shows something, right? So all entries, right, in a table must sum up to 1, right? That's a total probability. If you sum across the row, you got the marginal of X. You sum across the column, you got marginal of Y. Again, right, row or column here are relative, right? If you just sum across the appropriate dimension, then you got the marginal of the random variables, right? For example, you could have X, Y, and Z, right, together as a discrete random variable. Now, of course, representing this is impossible, like, you know, on a paper, right? Because there'll be a cube or something three-dimensional object. But we can still, right, symbolically talk about how you sum across all the Y and Z, then you get the X, right? You sum across all the X and Y, you get the Z, things like that, right? This is where your Calc 3 education must come in, right, to help making sense of this. But yeah, right? So you have the marginals from the joint, right? By summing across the other right, dimensions. All right. And then, right, the next topic is computing probabilities, right, from the joint. Or, right, the main message here is the joint table gives you everything you need. You just have to know how to extract information out of that joint table or joint PDF, whatever, right? For example, how to calculate probabilities? Well, the short answer is just sum over the appropriate region, okay? Nothing more we can say about that. Meaning, right, that I cannot tell you what the region, well, okay, I cannot tell ahead of time what the region looks like. And you have to read the region, right, to see what kind of values are appropriate. And of course, right, the region can be much more complex, like, I don't know, right? Even something like this is mile, right? That's a circle. But you can describe any kind of region you want. And again, right, Calc 3 would be something, right, that comes to mind here. Look at some popular regions that we can describe. But anyway, right? So, right, to give examples, right? And the examples here, right, the final numbers are irrelevant, right? What happens here is just basically, right, using the table above, you just sum up, right, over the appropriate values that satisfy the criterion you want. That's all there is, right? Any question about this? All right. So, right, then we kind of talked about the marginal distribution already, right? Because the table has a marginal distribution. But, right, basically, if you sum across all the other values, then you got the remaining ones, right? This is just really, right, the law of total probability, okay? So, but a message right here is the following, that you should be able to see this on your own, but it's worth emphasizing that the joint is a much richer, okay, source of information than the marginals. Meaning, right, knowing the two marginals in no way is equivalent, right, to knowing the joint. So to give you a right concrete example, right, these are the marginals, right? Now I will have infinitely many ways, right, to fill this table in a legal way that have the same marginals. Agree? I have literally infinitely many ways to fill this table to obtain the same marginals, correct? On the other hand, right, with this table, the only marginal that can come out is this. So the joint distribution decides the marginals, but the marginals do not decide the joint. Is it okay? And of course, right, one of the key information we want to get from the joint distribution is how they interact, including, right, independence. And this is probably where the point where you guys can appreciate, right? You can tell whether X and Y are independent from the joint distribution. If you're just given the marginals, you cannot tell, right? Because you just know how they act individually. You have no information on how they act together. Is that okay? Any question? All right. Now, when it comes to expectation, sorry, there's an extra equal here, right? So, yeah, right. You could, of course, right, compute expectation from the marginals. That's just definition of, right, individual expectation. But yeah, we'll see right down here. That basically, right, you could compute expectation of, well, we'll mention it down here. So I'm just kind of torn what I want to cover first. Okay, that's fine. Right. So this slide is just demonstrating how you can calculate, right, the usual expectation and variance, whatever, right? As you would have done, right, for the one-dimensional random variables we discussed. But there's a connection back to this that we'll talk about. But now, right, here's one point about the joint distribution. That basically, right, the joint distribution allows you to conclude about the interaction. And mind you, right, independence is just one concept, all right, among a lot of other things you can talk about in terms of interaction. But anyway, right, so the independence means that the joint distribution splits into the product of marginals, okay? That's really the key word. Joint distribution is a product of the marginals. And because this also works at the PDF level. And the key, right, is that it must split at all values. Okay, it cannot just split at some value. It must split at all values. So in fact, right, if the contrapositive is if it doesn't split at some values, then that means they're not independent. For example, right, let's take a look at this table. Well, 0.25 times 0.25, is that 0.05? Don't think so. So already, right, they're not independent. I don't have to check anymore. Okay, so just looking at this entry right here, I conclude that X and Y here are not independent. Okay. Conversely, of course, right? If they're independent, then all products must work, right, for all entries. Is that okay? Now, so, yep. So here's when the case, right, when independence plus marginals, right? So this right here is basically saying independence plus marginals is equivalent to joint. Remember, right, the theme before is joint is much more than marginals. But if you have marginal plus independence, then that's equivalent to joint. Why? Because you can reconstruct the joint from the marginal. This is actually the number one reason why independence is such a common hypothesis, right, among problems, theory, blah, blah, blah. The reason is, right, instead of giving you a joint distribution of n random variables, they can give you the marginals. Let x1 to xn be IID exponential, right? And then expect you to be able to construct their joint distribution from that statement. But of course, right, that doesn't mean that everything, right, have to be independent in the world, right? And of course, right, easy consequence from independence is if, right, x and y are independent, then expectation splits. Again, right, this is a student's favorite thing to do, in which they like to conclude the opposite, right? That if the expectation splits, then the random variables are independent, right? So let's put this message clear, right? Of course, one way to say this is expectation split, but what's another way to put it in terms of relationship between x and y? If expectation of x, y is equal to expectation of x times expectation of y, how do we classify this? How do we call x and y? We call it uncorrelated, right? Because the covariance is exactly the subtraction, right, of expectation of xy. Right, you actually start seeing the covariance being more active and more relevant here, because exactly, right, covariance only comes in when you can calculate this term, right? We introduced the covariance before as a kind of a warning for you when you take the variance of the sum, right? But as you can see, to calculate expectation of x times y here, you need the joint distribution of x, y. That's the slide right here. Okay. But anyway, right, this signals that x and y are uncorrelated. Now, right, of course, the question then is, are independence and zero correlation equivalent? The line here, right, it says independence implies zero correlation. Do we have the opposite, the reverse implication? Is there an example of random variables that have zero correlation, but not independent? The answer is yes, right? Take a random variable with three values just to make sure that they are, you know, when you I squared, it doesn't become a number, that's all, right? Let's say take three values, right? We're probably 1/3 each, okay? Now, then what is x squared? X squared, right, takes on value 0 would probably 1/3, right? And 1 would probably 2/3, right? Okay. Anyway, I hope it's clear that these guys are not independent, right? No way x squared and x can be independent, right? You think about it. But what's the covariance between x squared and x? Right? Expectation of x is 0, right? Because it's symmetric. What about x cubed? Well, surprise, surprise, right? X cubed takes on exactly the same values with the same probability. Agree? So expectation x cubed is also 0. So this is an example, right, of two random variables with zero correlation, but are dependent. Is that okay? Any question about this? Okay. All right. So anyway, right, this slide actually talks about how you can calculate something like expectation of x times y, right? For any function of the x's, to calculate its expectation, well, you would just do the obvious, plug in the function at those values and multiply with the joint distribution. Again, right, this is a law of unconscious statistician, right? Probably it's hard to keep saying that by now. But the point is, right, this is not directly from the definition of expectation, okay? But anyway, right, it's very easy to use and we'll just use it without worrying about, right, the proof of that. Okay. So for example, right, expectation of x times y from the table above, right, that this table we just talked about is 4.45, right? You just have to, and notice, right, it's really without softening it, right? It's a tedious thing to do because you really have to look at all pairs, right? X times y. There's nothing else you can do, okay? But at the end of the day, right, you see that that's the expectation of x times y. Expectation of x and expectation of y comes from the above. And so, right, they're not independent, right? So of course, we already knew they're not independent, right? From the fact that these two entries, right, do not multiply to each other, to this, right? But that's just a reinforcing, right, thing. Okay. Any question? Now, just a sort of like on this, right? We compute expectation x and y based on the marginal, which right should not surprise anyone because that's how definition how expectation works. However, right, this formula right here gives you another way to calculate, say, expectation of x. Because, right, you can view phi of x1, xn here as equal to just x1. Right? You can have a function that maps only to the first coordinate. And from that point of view, then expectation of x can be equal to sum over x, p of x equal to x, y equals to y. Sum over all x and y. All right. This actually is, of course, a different formula from the marginal calculation. Because, right, this formula uses a joint. But if you look at it very closely, right, it reduces to the marginal. How? Because if you sum over y's here first, right, the x factors out. So it's really become sum over all x p of x equals to x times x, which is expectation of x, right? So this is just emphasizing that you can use a joint distribution to calculate the marginal distribution. Of course, it's included in different ways, right? Neither way is more valuable than the other. But this way would avoid calculating the marginal out explicitly, right? It would just sum over all entries in the joint table, okay? And it has some use when it comes to the joint PDF, because sometimes we don't need to calculate the marginal. We're just going to calculate things out straight. So like that. All right. Any question? All right. Okay. So that's all we have for the jointly discrete. Let's take a look at the problem set. All right. So we'll start out, right, just exploring how to write down the joint PMF of a certain random variables. There's nothing really crazy here, right? This is just going back to probability calculation under, right, I guess the title of finding the joint mass function, right? So, but it should be gone over at least once so you understand that, right? This is how people would calculate, let's say, the joint mass function for some new random variable. All right. So we won't waste time going over all entries, but let's say, right, for example, tell me how will you calculate this entry for part A? Well, this means the first ball selected is not white, right? Is red, and the second ball selected is white, right? And so that would be what? First ball selected is red, and second ball selected is white, right? So that's like that. And right, similarly for all other entries, right? You just do that. So it's really a 2x2 table, right? For this joint distribution. All right, any question? And for the B part, right? It will be a three-dimensional distribution, right? Where each of them takes on 2 entries. So in total, you will have 8 entries, right? To list out the values for. But you should notice that some of the entries are equal, right? Like 0, 1, 1, 1, 0, 1, 1, 1, 0 kind of thing. So it can collapse down, right? In terms of the writing by symmetry, right? Like that. Any question about this? All right. Now, this is still right, sort of an exercise in writing down the joint mass function, but it kind of put a twist on this, right? If the white balls are numbered, right, then how would that be different from the answers in the previous part? For example, again, right? Say part A, what's probability of y1 equals to 1 and y2 equals to 0? What would that be? So, right, it's similar to the previous one where you can do the law of multiplication, right? Except that now you are focusing on just one particular ball. So the product, right, is still there, right? The product is still there like that. Except that, right, the numbers on top is not going to be 8 and things like that, right? But it will be combinatoric expression because, let's see here, if the white ball is a number, so you choose 3 balls, right, for the yeah. So basically, right, it's going to be like this because, right, basically these are 2 specific balls, so there's only one choice, right? And 11 choose 1 exactly is in the choice for the remaining ball, right? Being, you know, whatever, right? Whichever color. Right, out of the 11 remaining balls, you just choose 1 ball, right? Things like that, okay? Now for the joint of 3 of them, right? Same thing, but of course, right, for example, if the 3 balls are chosen like this, then there's only one choice because, right, that's only one way to do so, and so on, right, for the rest. All right, any question about this? Okay. All right. So yet another variation, right, on this problem, where now the the selection, right, is with replacement, not without replacement. So how would things change? So, right, how things would change here is actually things will be like, you know, independent, right, ish. So you can just multiply the probability across because you will be, well, it's still a lot more multiplication, right? But now you don't have to account for the fact that a ball has been taken out. You don't know how to subtract the number of colors that has been taken out, that kind of thing. Right. All right. Any question about this? Okay. All right. So let's take a look at this question. Now, first of all, right, the question may be a bit not easy to understand, especially in the role of n and x, right? So to check or to test the understanding, right? Can someone give me an example of a specific trial, a specific experiment, and explicitly point out what n and x are in that experiment? What would be an example to illustrate this description? Give me an example for n and x in an experiment. The example, right? An example that can be easily come up with is, let's say, k equal to 6. And you could make the pi not equals to not equal to each other if you like. But so 6 here, right, would represent, let's say, a dice throw, right? But this is a weird dice, if you will, where the dice is numbered from 0 to 5. But that's okay, right? Because you know you don't have to, right, label the dice from 1 to 6. It can be 0 to 5. Okay. And you can throw in numbers that are not equal to each other if you want. 0.2, 0.4, right? That's a bit too much, right? 0.1, whatever, right? Etc. Let's say this is 0.2. Okay. To as a probability of the dice roll those numbers. Okay. So what is the experiment? The experiment is you keep rolling the dice, right? Until you see a non-zero face comes up. Okay. Then n, right, is the number of tosses you need to get that. All right. And what is x? X is the result, the specific result of that non-zero face, whatever that is. Okay. And what's the sort of the message here or the point here? The point here, you should kind of try to contemplate in this experiment, does X and N have any connection? Does X depend on N in some way, or does N depend on X in some way? Does the knowledge of N give you some information on X and vice versa? What do you think? Say you know that it took 10 tosses to get to a non-zero phase. Does that give you any information about what that non-zero phase is? Well, as you can see, right, as suggested in this question, the answer is no. I mean, meaning they're independent, right? Knowing the result of one of these, like number of tosses, doesn't affect the result, the actual value of the toss, and vice versa. Okay. But the thing is actually, right, if you read this question, maybe the intuition is they have some connection to each other, right? And so the point here is you have to prove or to establish the independence beyond all doubt by using, right, the very definition of independence to do so. Okay, so the question here is about establishing that independence via rigorous calculation. And so the three parts, right, is meant to do that. Okay, so let's start with part A, right? What is probability of N? What is the mass function of N? In terms of the PI, of course, right? The answer is abstract here in terms of the PI. What would that be? Or better yet, right? What kind of random variables? What kind of random variable is the N here? What distribution does N have? Well,
Geometric.
yep, geometric one. When you say a random variable, you have to give parameters, right? Geometric what? What's the success probability? What is the success here? Success is to see a non-zero phase, right? So success is 1 minus P0. Therefore, right, it will be P0 to N minus 1 minus P0. Any question? All right, what about B? Now, B would look at the mass function of X. Notice, right, X as the value, right, of the non-zero phase is like a conditional, right, distribution. Because this is not a dice toss, right? This is that dice toss conditioned on the fact that, you know, the dice cannot toss into a zero. Because you know that, right? So what distribution is it? Notice the J values, right, is only from 1 to K, right, excluding 0. So what's the probability for these? Is it PJ? Is it simply PJ? The answer is no, right? Why not? Because notice X here is only allowed to take values from 1 to K. So if you sum PJ from 1 to K, right, you will not get 1 because you're missing out P0, correct? So the sum over PJ from 1 to K is not 1. Right. So what's the right answer here? So remember, it's a conditional distribution, right? This is conditional on the fact that so it would not be surprising that it's a division, right? PJ divided by 1 minus P0 for J from 1 to K. All right, any question about this? Okay, so now part C asks you to show that they're independent, right? So I assume this is the first time you're asked to show two random variables are independent, maybe, right? Rigorously. So let's just pause and ask, what does it take? What must you show here? Because you can show something, let's say, bogus, right? And it won't count, all right? So what do you need to show that these two random variables are independent? What do you need to establish? Well, the answer is simple here. The mantra is show that the joint is the product of the marginals. That's always the case, whether it's continuous, discrete, whatever. Show that the joint is a product of the marginals. If you can do that, they're independent. If you can't, they're not. Okay. So now how do we do that? Notice, right, we have got the marginals from part A and part B, right? That's the point of part A and B. You can plug them into here. What about the joint? Notice, right, a funny thing can happen here. Pretty funny, in fact, that for the students who would just want to finish the problem and go do something else, well, easy, right? They also will write down this times that for this side and say, I got the proof. Okay. And that's actually what's called a BS proof, because you assume, right, the result. Because you assume that somehow this is a product of these two and you plug that in here. So an honest proof would require you to calculate the joint here somehow, not assuming this. So you have to look at this joint in of itself, right? And how does that work? How do we calculate probably n equals to n and x equal to j in of itself? Well, the answer is actually pretty easy. You just have to read what this means. N equals to n means it takes you n tosses, right, to get to the non-zero phase. So it must be p0 to the n minus 1, right? First n minus 1 must be 0. But what's the last one? The last one must be j, right? Because you know that x equals to j. That's it. Right? That's the joint. Now, is it equal to this times that? Well, you bet, because these cancel. You understand? Any question about this? All right, so let's give you a proof. Sorry, let's give you a quiz, right? And then we'll take a break. So the quiz, let's say, will be this question, right? Part A. For the quiz. Any question before we take a break? All right, so let's resume at 7:05.
Professor, could you scroll up to problem one for like
Oh yes, 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 yes. That's a good thing. So absolutely. Sorry. No, absolutely. So okay. So how about this? So you know what? There's a quiz. Who cares? Let's change this to the quiz. All right. Sorry. Let's change this so that you can have the problem one. All right. So let's not do problem two.
okay, yeah.
Yeah. Okay. Thank you. Okay, any question before we continue? All right. So I guess the next topic will be the joint PDF. All right. So the joint PDF, right, is like the joint PMF and PDF, right, together, meaning that it's a function, right, of n variables. It's non-negative and multiple integral, right? Our dimension that is of this over, right, the entire region is one. And right, whatever we said about density also works for the joint density, meaning it's not a probability, right? It only serves you as a likelihood, but now it's a joint likelihood, right, of the random variables. And right here is, I guess, one of the more famous joint density is the joint normal. But basically, right, a joint density will be a surface, right, over the region that is a support, right, of the random variables. Now, of course, right, the region can be an infinite region, like the joint normal here. It's going to be actually, it's not from -2 to 2, right? This is just a snapshot. It actually extends, right, all the way, okay, to the entire plane. But anyway, right here, we're just trying to capture the sense, right, that it is a surface versus the spike, right, the spikes of the joint PMF. Okay, so right here is a famous, right, like again, well, that's a joint normal, but the one you saw before is basically joint, standard normal, if you will, right? So no correlation, no variance, that kind of thing. Variance is 1, means 0. But the general case is right like this, where right you have the means, and you have the variance, or rather the standard deviation, and the correlation, right? And it's one big. Let's not call it ugly, because there's a way to write this very nicely. But in general, you can see that basically joint PDF doesn't have to be a very nice object to look at. Let's say it's not a very simple object to look at. Let's put it that way. Okay. There are a lot of parameters to keep control, to keep track of. And right, integrating or working with joint density is not let's say, not a walk in the park. Okay. But well, that's why you learn, right, how to deal with it. Okay. So, right now, these are both yes, right? You can answer. And actually, the point is you can answer this question for any joint PDF, not just the joint normal. The joint normal is put here as like an example where it's kind of difficult because of the calculations and not because of the concept. All right. But the answer, the abstract answer is yes for any joint PDF. You should be able to answer these questions. And we'll show you how. Okay, but easier joint distribution to work with. Well, not yeah, right, is the uniform. So this is like a generalizing, right, of the uniform over a line segment. Now we have a uniform over a region, right? So basically, uniform means the joint density is a constant, right? Doesn't change. What is that constant? Well, the constant is 1 over the area, right? Because we're looking at the formula of the volume, right, of the cylinder. Right? If you have a cylinder, then the volume is area times height. So therefore, right, height is 1 over, and volume, of course, right, is meant to be 1 because that's the probability, right? So height is 1 over area, right? So, but and again, right, you have the analogy of, right, proportional. meaning that to calculate probabilities of the uniform, the nice thing about it is you just have to look at proportion. So this simplifies, right, calculations even for this part, because this kind of boils down to some geometrical calculation. You can use geometry instead of double integral, right? This allows you to use geometry. Okay. So, but that doesn't mean that, right? So again, just don't get used to this fact, because for general density, just like for general random variable, you have to integrate, right? So integration is really a fact of life. But when you have the uniform, then you can make your life easier. So you don't have to work that hard. But that really shouldn't be confused with, right, the general nature of things. Okay. So, and also, right, the uniform here on a region demonstrates a very nice fact about, or the complexity, right, about how, well, if it's a uniform, right, on the line, the uniform we talked about before, and there's nothing much to talk about it. But when you have a uniform on a plane, then suddenly the shape matters. The shape will control the interaction between x and y. So even if it's uniform, right, the region will not make it the same kind of uniform. Case in point, right? Yeah, right. So I guess let's start out slowly, right? The first thing to do is, right, look at how to compute probabilities from joint density. The answer is, right, instead of adding, you would integrate, okay, over the region. Emphasis, right, integrate. So these are double integrals, triple integrals, and whatnot, okay? And yes, you will have to do that, okay? So, but that's all there is. That's all that can be said about it. Now, of course, in some cases, you can use geometry, like here, right? If you have a uniform on a unit square, then, right, if you look at this region, its area is 1/4, right? Because, right, 0, 1, right, less than 0.5 for x and bigger than 0.5 for y is this part right here, right? So of course it's a tiny square, so you can do that, right? And what about this? This actually, right, we didn't give an answer here, but if you take a look, right, and we'll look at this problem a lot, so might as well look at it, right? This means x minus y is equal to, or rather, right, let's switch it around. Y minus x is equal to plus minus 0.5. That means y is x plus minus 0.5, right? What are those two lines? Right here. Right? So this region is captured by these two triangles here. All right, what's that area? Easy, right? Double the area of the triangle. Triangle area is base times height, 1/2. So it's base times height. So the answer is 0.5 squared. Any question about this example? All right. The same one-ish, but we just make a tiny switch. Unit circle now. The story is no longer that easy, right? And again, we don't give an answer here because we don't mean to, work out everything, blah, 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 right? During a lecture, you can just do that on your own or something. But let's pay attention, for example, right? If you have a uniform on a unit circle, well, unit circle is, well, we just shift it over here, right? Like that, okay? So where is this now? in terms of a unit circle? Well, this will become this part. Let's enlarge it, right? Here we come this portion. But notice, right, it's a circle. So this portion right here, well, you don't have a geometry to decide what that portion is. So notice, right, it's the same region. And the density is very easy, right? This is 1 over pi because the area of the circle is pi, right? The area here is 1 over quarter. Sorry, the area here is 1, right? And we don't even care for that fact because we just, yeah, we do because we look at the area, right? The proportion. But notice, right, the region here, the answer is very easy because you know the geometry. The answer here, well, not going to be so easy, even though it's a uniform. So you probably have to do, I don't know, some polar coordinate and whatnot to calculate this out, right? And we're not claiming that this is an easy or hard integral. That's not the point of the example. The point is integration is not avoidable. It's not avoidable, right? You know, even for a simple distribution like a uniform, if the shape of the region is complex. All right. And these two, right, should kind of give you the comparison between two uniforms, but very, very different properties. All right, any question about this? Okay. So now, right, let's talk about the concept of the marginals. So for the joint PDF, the marginals, right, of course, can have an expression, but you need to do calculation. So here, for example, right, the idea is, right, the PDF, the joint PDF is a surface, where the marginal is a curve, right, on each. And it does try to say that the marginals of the joint normal are normals, which could be surprising, could be not, who knows, right? But yeah, right, it's just trying to demonstrate that fact. But yeah, right here, this rather complex expression just try to say one thing, right? To find the marginal of the ith coordinate x of I, you integrate out all the other variables. Right, notice this is a function of n variables. If you integrate out all the other variables, then you get the remaining one. All right, just some reality check here. For example, let's say we do know how to integrate x plus y squared dx, for example, right? That would be some case like this, right? This would be finding out the marginal of y, right? Which I leave out the limits, right? Notice the limits here has to be in the appropriate region. All right, this is over an appropriate region. What's the reason? The reason, for example, is, again, let's look at the two examples here. If you have the uniform on the unit square, right? Then for every, let's say, x value, right, like this, then the y goes from 0 to 1. For every x value, right, the y goes from 0 to 1. Sorry, what I'm saying. For every y value, right, the x goes from 0 to 1. Right, and vice versa, right? For every x value, the y goes from 0 to 1. Right, so there's no interaction between x and y. And in fact, right, you see the unit square here, the x, y are independent. But for the circle, right, for this x value, y goes from here to here. For this x value, y goes from here to here. For this x value, y from here to here. So the limit of integration, let's say you integrate, right, 1 over pi dx to find the density of y, right? This right here, these two limits will be function of y. Do you understand? Because for a fixed value of y, right, the x can only move from someplace to someplace. All right. Again, right? These are things that you should have seen in Calc 3, right? But we're just repeating here for that. So, right, the concept here is, as far as probability is concerned, just integrate out the other variables. But that's not the end of the story, right? In the actual problem, you will have to do a lot of work. The first of these is to find out the appropriate limits of integration. Okay. Any question about this? Well, actually, case in point, right? Let us. I'm not sure if this is 8.1 or 8.2. Let us look at the problem set here. This is the problem set after this, but do I have this? No, anyway. Let's do it on our own. Let's look at XY, right? Uniform over unit square. What are the marginals? And repeat for XY uniform over unit circle, right? What are the marginals? So, right, we will start with the joint. So the joint for a unit square, right, will be 0, 1, right? 1 like that. So basically, right, for this, right, let's say this is question 1, this is question 2. The joint, right, is really just 1, x less than 1. That's a joint distribution. That's a joint density. All right, any question about that? And so to find the marginals, right, you would take the joint, which is 1. Well, let's just write it out, right? Integrate out the other variable for the appropriate limit. So for this fixed, so when you do this, right, the marginal, this one is fixed. And this is integrate over. So that's kind of moving, right? So you have to decide where it's moving from where to where for that fixed value of x. Well, but you see, right, for this fixed value of x, the y will move from 0 to 1. For this fixed value of x, the y from 0 to 1. So it's always from 0 to 1. Right? And so, of course, the margin was 1. So the answer is just 1. Again, don't let the simplicity of the answer fools you, right? The only reason is, of course, this is simple. But, right, similarly, f sub y of y is the integral from 0 to 1 of the joint dx, and that's also 1. So what have we said? We said that if x, y are jointly uniform on the unit square, then x and y are marginally uniform on 0 to 1. And what's more, they are independent. Why? We haven't said this, but sort of, we did say this for the discrete random variables, right? Jointly discrete. The joint is a product of the marginals. Therefore, they're independent. Okay? Now, what's the story with the unit circle? Well, for the unit circle, right, then the joint density is 1 over pi over the region, like that. So already you see the description is very different. All right. And so how to find the marginals? Well, right, same concept really, but, well, not really, same concept, but very different execution. So still integrate, right, the joint, integrate the other variable, right, out of the joint. But again, right, so for this fixed x, where does y run from? Well, for this fixed x, you see the y would run from here to here, which is what? The top here, of course, is square root of 1 minus x squared, right? And from this is minus square root 1 minus x squared. All right, so it's really minus square root 1 minus x squared to square root 1 minus x squared. And with that being 1 over pi, the answer is 2 over pi square root 1 minus x squared, or x between minus 1 and 1. Question, is x uniform? Answer, obviously not. Okay, so here, right, you can have x, y jointly uniform, while x and y marginally are not uniform. That can happen, all right? So again, the joint and marginals are not that connected, not that simply connected in terms of whatever guesses you want to throw at it, right? And of course, similarly, right, because it's a symmetry really, is this. And so are x, y independent? Of course not, right, for the uniform circle, uniform over the circle, right? Because the product of the marginals is not the joint. So that's the demonstration of calculating the marginals from the joint. Any question? All right. So, right, I guess I just mentioned about the independence criterion. So there's nothing new there, right? Just repeating, replacing, right, the PDF, the PMF for the PDF. All right, so here, right, is another example where you have the bivariate normal, right? The one that we just talked about in the above. You can show that x and y have this marginal distribution. And so the product of these two is not the joint, which is this one. Right here, right? What's missing, you ask, or what is wrong? What is wrong is the term right here, this row term, and this cross term right here. That in the language of the bivariate normal, that's exactly the one that controls the interaction. Okay, so they're not independent. This part right here is like the marginal of x. This part right here is like the marginal of y. But you have the cross term, and of course then you have the row, right, playing the role of the correlation. Okay, any question? And here, right, this is special, all cap. And I don't mean to be dramatic, but yes, special, all cap. Why? Because it say they're independent if and only if the correlation is equal to 0, right? I have shown to you right in the above, I have warned you strongly that zero correlation does not imply independence. So here is an example, and probably the only example I know. I'm not sure I know of another one. There might be, but I don't know. Where zero correlation implies independence for joint normal distribution. That's why the joint normal has a special place. I mean, not why, but one of the very nice properties it has. And probably also the number one reason why people confuse between zero correlation and independence, because joint normal is used everywhere, regression and things like that. And in that context, it is correct that zero correlation implies independence, but it's not true in general. So that's why, right, we have to point out this is a very special result with the capitalized everything. All right. Any question? And the point here, right, is we don't have room in this, but you can take this expression right here, and you can easily see if rho is equal to 0, right, then this is 1, and this term is out. This term is out. So it's really a product of two marginal normals. That's all there is. Okay, so the structure of the joint PDF allows for that. That's all there is. Okay. Okay, and we just talked about this, so that's just reiterating, right? The uniform on the unit square, and the uniform, right, on the unit circle. Okay. Any question? Expectation follows the same drill, right? Except that, now it becomes a multiple integrals, right? Instead of a multiple sum. Right. So here is where, I guess, probably from economy of writing, right? Here we point out that expectation of x can be calculated in two ways, by the marginals or by the joint, and they are the same thing, right? So sort of, I just pointed out that, right, in the above. But this formula, right, accommodates all kind of functions of x onto xn, right, including the one where it just mapped to one coordinate. That works as well. Okay, right. So again, going back to our stock examples, right? For the unit square, you see expectation of x times y doing your favorite double integral. And notice how this one split in terms of the calculation. That's a strong sign that they're independent to begin with. But anyway, okay, you got 1/4, which is of course a product of the two expectation, right? This is the expectation of x, expectation of y, which is of course right here. So again, right, no surprise here. The structure just carries through in all the calculations. For the unit circle, right, notice this does not split. And by split, of course, right, I mean an integral entirely in x and an integral entirely in y, right? But let's ask, right, why not? Here, x and y like that, why can't I split them? It's really x times y, right? I can split them, right? What prevents the split?
I mean, you could change to polar to split, but I can't really say why you can't split. It's just
No, if you switch to polar, you cannot split either. Oh, you mean the r and the theta are independent? Oh, that's a very interesting observation. But notice, right, what you're saying when you say split to polar, there is a concept like that in probability. But what you are saying is that now you switch to a different pair of random variables. And you claim that these are independent, which I agree with you, but that's a deeper fact that we need to investigate on in ourselves, because these are two different random variables, right? So this is actually the topic of the next lecture, which I plan to skip because we have not enough time. But if you are interested in this is called transformation of random variables. And you're claiming that if you have a uniform on the unit circle, then you transform them to polar, then the polar are independent. But notice it's a very different claim, right? From saying the x and y are independent, these are a different claim. Just as with the unit square here, if you transform them to polar, then the polar parts won't be independent. Okay? So while your statement is correct, and it's a very, very good statement, it's not right about what I'm trying to say here. So when I say it does not split, I mean the x and y do not split, right? And they do not split here exactly because of the region here, right? Because this region is written like this just to make it simple, but you can also check that this is not a rectangular region, right? So you do the x first, so x goes from 1 minus y squared to y squared. And then y go from -1 to 1. So this region, right, does not allow you to make that split. That's all there is, right? But anyway, right, the expectation of the product here is 0. Well, it's clear the expectation of x and expectation of y is not 0. So that's not the same. Wait, hold on. You know what? This is weird. They might be 0. Hold on. This is actually very interesting. So here expectation x times y is 0, but if these are the marginals, and because of symmetry, right? If you integrate, let's say y squared 1 minus y squared from -1 to 1, you do get 0 because it's an odd function. So here is actually another example where x correlation of xy is equal to 0, xy not independent. This is another example. This is exactly an example at the continuous level, right? The example I gave you was a discrete example, but this is an example at the continuous level, right? Where you can have random variables that have 0 correlation but are not independent. And this is actually more beautiful in the sense that it's okay. It's a different taste in the sense that these are, right, x and y here kind of are two different coordinates of the circle, right? Rather than like x and x squared. So it has a different taste. But yeah, this is a very, very nice example where x and y are not independent but have 0 correlation. Right. Any question? Okay. So just repeating, right, the fact that expectation is linear, but now, right, you can prove or you can understand why expectation is linear. Why is that so? Because essentially it's a whatever integral after sum, right, multiply with the joint density, right? And you see, basically the sum, the integral operator is linear. And that's why, right, the sum will split. So that's why, right, doesn't matter what f is, this will split. And that's why it says does not require that xi's are independent. So long story short, the linearity of expectation is because of the linearity of the integral operator or the sum if you're doing discrete, right? And you see, it doesn't care what structure of the joint density is, right? Whether this splits or not doesn't matter. The sum here will split over the triple integral or the multiple integral. All right. Yep. So, right, I was saying about how, right, independence implies 0 correlation, but not vice versa. However, there is a stronger version of the expectation split, which is probably not useful at your level, but is useful at a high level. That says if expectation splits for any function phi in x and phi y, then you can imply that x and y are independent. It goes both ways. So I guess here I want to say if only if. So that's a more advanced statement. Okay, but this statement is not useful at your level because you might use it wrong. This is only true. This is true if this is true for all phi and psi. So there's this kind of quantifier, and quantifier is one of the things that most is easily misused. Okay, I guess for the inexperienced. So, but this is true if you know how to use it. So for now, right, it's safer for you to use this. This does not imply that x and y are independent. That's it. Okay. All right. Yep, covariance, right? And I think right, you asked about the meaning of covariance. So I'll explain it once upon a time, right? The covariance measure the linear dependency between two random variables, meaning that if y is a linear function of x, then the covariance, right, is the correlation, right, is 1, right? But if x and y are not linear relationship, then the covariance could be 0, and it doesn't say anything. So basically, covariance, right, is a measure of linear dependence. So I guess here I should say what's correlation. So correlation of x and y here will be 1, right, if a is positive, and will be -1 if a is negative. And here, right, correlation of xy will be 0, even though, right, y is a function of x. So covariance also has that meaning that it measures only linear dependency between x and y. Okay. Again, this is kind of a story that's closely connected to independence from that point of view. So these two stories should be told together. Any question about this? All right. Yeah, right. I was saying this is Pearson correlation. There are other definitions of correlations. All right. So in terms of covariance, right? Well, we're not going to harp much on covariance in this class because it's not really object of study. You will see covariance more in, I don't know, right? I mean, what's it called? The experiment design class, right? Where somehow I forgot the name, but there is some kind of covariance object that you explicitly construct. But anyway, right? There are two properties of covariance you should know that sort of like somehow people tend to miss. The first one is a covariance of a random variable with itself actually is the variance. So in that sense, the covariance is a generalized object of variance, if you will, right? So variance is actually covariance of some object with itself. In fact, covariance actually acts like an inner product, okay? Inner product of calculus 3. Covariance acts like an inner product. And that's why when you have an inner product of something with itself, you actually get the norm, the L2 norm, the length, the variance, okay? For this to properly work, you have to kind of normalize everything to mean 0. So you have to subtract x away from with a constant. You want to shift everything back to mean 0. But beyond that fact, then covariance acts exactly the same as an inner product. And so from that point of view, right, covariance is a bilinear operator, meaning that, right, it's linear on this coordinate and also it's linear on that coordinate because it's exactly like an inner product. So these are the two less well-known facts, I guess, for students, even if they have heard of covariance. But notice, right, these do not work at a correlation level. So that's why correlation is statistically meaningful, but mathematically is not a very nice object to operate with. Covariance is not statistically meaningful, but mathematically it's very nice to work with in terms of its linear kind of properties. Of course, right, covariance is the essential ingredient in variance of the sum, right? Just like the inclusion-exclusion formula, right, is there. It must be there, right, for the formula to work. Again, just kind of pushing on the covariance idea because, we only have a chance to discuss the covariance in the joint distribution context. A very important object, right, in, let's say, statistics, or let's say higher, I don't know, probability classes, a covariance matrix. And so, right, the covariance matrix is like the generalization of the variance object in one dimension, right? In one dimension, you have variance. Then in multi-dimension, you have covariance matrix. It supposedly captures the joint distribution at the second moment level. Doesn't capture everything, but it captures something. And the covariance matrix has some very nice property of its own, like it's symmetric definite, positive definite, blah, 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 so on and so forth, right? What kind of class would deal with it? Again, the name escapes me for now, but like there's certain kind of courses that would sort of go on in the covariance matrix. Yeah, I mean, like multiple linear regression would have to study the covariance matrix in very much details, for example, right? But just pointing out this object, in connection to variance, but not something we study in this class. All right, so that's all there is for this lecture. Let us go back to the problem set. All right, so here we are, right? So basically just working with the joint PDF, right? And while there's nothing much here, right? The point is you need to know your multiple integrals. All right, that's all there is. And set them up correctly. So this is, for example, right, over a rectangle. So nothing much to do here, right? Besides setting up the right integral, right? So part A, for example, right, is about verifying that this integral is 1, and what's inside is always non-negative, right? You need to verify both of these for part A. For part B is the integral from 0 to 2, right, of that density dy. Right? You will get a function of x out of this. Part 3, well, yeah, let's see. Let's pause here a little bit. What kind of integral will give us part 3? What do I integrate and over what? Well, can I integrate, let's say, dy dx, where y runs from 0 to x, and then x runs from 0 to 1? Would that be correct? Well, what is the region? The region is x from 0 to 1 and y from 0 to 2, right? And the line y equals to x is here, right? So x bigger than y is this region, right? So to integrate y from 0 to x, and then x from 0 to 1 is correct. That is correct, right? But notice, what if the question got switched to probability x less than equal to y, let's say? Of course, you say, right, if I know this, then I can just do 1 minus that. But suppose you set up the integral by itself, and let's say you do dx dy, and let's say x goes from 0 to y and y goes from 0 to 1. Is that correct? The answer is no, right? This integral is wrong. Why? Look at this, right? Here, if you look at this region, right, which is the region x less than equal to y, right? You see that x goes from 0 to y only for the values of y between 0 and 1. For y from 1 to 2, x go from 0 to 1. So this limit integration is wrong. Okay. So in fact, right, if this was the question in part C, then you should still switch back to calculating this region because the limit of integration is easier. And then you do 1 minus it to calculate this. If you want to integrate over this region, you cannot avoid doing 2 integrals. Does that make sense? So I just want to point that out, right? So you better be mindful of this. The rest, right, are the same. So, for example, right, E is the integral, right, of x, the double integral, right, times the joint density, dx dy, right? Well, x would go from 0 to 1, y from 0 to 2, and f 0 to 1. Sorry. I guess you want to do dy dx first. You can do dx dy. Y x goes from 0 to 1, and y goes from 0 to 2. So notice, right? For example, in all these questions, right, the decision whether you want to do dx dy or dy dx may matter, right? That's by the nature of the PDF. The theory doesn't give you any clue about it, right? The theory just tells you to integrate over the appropriate region. Whatever the appropriate region is and what's the best way to integrate over it is from your education, right, in Calculus 3. Is that okay? But every technique, right, from sketching the region to switching the limits of integration, deciding whether the x dy or dy dx is better, these are all relevant, right, and assumed for this material. Okay with this? Any question about this? All right, so if not, then let's stop here, right, and continue on Wednesday.
Professor, I have a question about the normal distribution.
Yeah.
So will we be given the table during the test?
No, remember, I said for the normal question, the answer will stop when you give the answer as the CDF of the standard normal.
Sorry.
The
Didn't break
every
that up.
every answer abstractly will have to be given as the CDF of the standard normal. Beyond that, no one cares. I don't care. Yeah.
Okay, understood. All right.
Mhm.